Welcome back, friends. So, we have been dealing with examples in QED, and in the last lecture we also looked at another potential. So, what we are doing is essentially how to make a potential dynamic essentially. So, that is the point we tried to do. So, we actually assume that we can make it dynamic, but we did not show you the method, but anyway we showed you now essentially that you take any potential in quantum mechanics and then write the Fourier transform of it, and that gives you a propagator, and that gives you a propagator. Right now we are still not using quantization and the particle interpretation essentially. Okay. So, but that gives you lot of information, like for example for the electromagnetic field what we have seen is that if you take the static potential essentially, if you take the static potential and it gives you 1 by q square term essentially in the Fourier mode, and from that you can calculate the Coulomb scattering cross section. But if you want to make the field dynamic, what you have to do is essentially that we can write the propagator for also the photon field, which I think we have derived it earlier, but I have derived it. So, I did one example of electron positron scattering, electron proton scattering sorry, where the proton field acts like a source for the electromagnetic field, and you put it back into the electromagnetic field source term as a source term, but you can now treat the electromagnetic field source term to be delta function, and that gives you the propagator of the electromagnetic field, and that is nothing but 1 by q square. There is nothing surprises in it, we already saw it. That gives you 1 by q square, and this gives me because the del is nothing but q square and a mu, you can write it down in terms of what do you call in the Fourier modes, and that gives you the propagator. So, this is extremely simple. Now we consider, now this gives you the propagator, use the propagator, calculate your matrix elements and so on, so and compute your cross sections and everything. Now we took a completely radical thing, we have been so far focusing on potentials which are like electromagnetic potentials, but we now said are there any other interactions which are equally important like electromagnetic interactions with Dirac fermions, essentially with Dirac particles. So, Dirac particles with vector like particles is the QED interaction. So, vector likes because so two fermions, so these are two spin half particles, can go either into a vector which is spin 1 or a spin 0 essentially, it can go into a spin 0 essentially, that is a scalar. Now we can directly start with that you can also have a scalar interaction. So, it will be something like psi bar psi phi, that is a generic Yukawa interaction. Okay. Okay, that is a generic Yukawa interaction with two Dirac fermions with a scalar interaction with a scalar, but you can also have a pseudo scalar like interaction like the example which I am telling you right now. In this case what is happening is that the potential we are considering is the Yukawa potential, and the Yukawa potential, and if you want to make it dynamic, this is the static thing e power minus mu r by r. The mu sets the range of the potential, it sets the range is given by 1 Fermi, which is essentially the size of the nucleus, rough size of the nucleus, and it is also set by the Compton wavelength of the mediator, or 1 by m or 1 by mu, essentially mu is nothing but the mass of the pion like I mentioned it essentially. In h cross and u, c is equal to 1 units. Okay. This is nothing but h by mc, and the lambda pion Compton wavelength is h by mc. Now, so if you do this and then write down the corresponding Fourier mode, you get the propagator of the Klein Gordon propagator. So, the potential is generated by the exchange of a scalar field. So, with this you can write down say for example, neutron proton scattering, neutron scattering, and so on, proton scattering with a pi 0, and similarly you can think of pi minus with anti protons and so on, so essentially. Okay, good, this is good, but one subtlety here is that the pion is a pseudoscalar current. So, the pion is a pseudoscalar. So, you instead of psi bar p, psi bar p, psi p, you also need to put in a gamma phi. Okay, this is a gamma phi essentially. So, theories with 2 fermions and 2 scalars are called Yukawa interactions. The one example, this is with the pseudoscalar interactions is the pion essentially, is a pion neutrons nuclear scattering essentially. So, the pion nucleon scattering is one of the example. Okay, good. Now, let us address the question from higher order corrections. Now, how can we make higher order corrections consistently? Are there any problems? If you want to do second order in perturbation theory, how do you go about going in out essentially? Second order in perturbation theory, now you can write the Green's functions and everything. You have E square term which we have written it earlier essentially, and so the what we have calculated so far is the E vertex essentially. So, but then there is the E square of the in the series, in the Dyson series or any of the other series, there is the E square term essentially. So, that means that there are higher order Feynman diagrams which you can draw. Say for example, instead of one photon you can exchange 2 photons. There could be a photon which is exchanged and come back and so on. So let us take the simplest example of say for example electron scattering. Okay, electron scattering, it is a simple example. So there is an electron comes in and there is an electron goes out. So you can exchange 1 photon, that is one problem essentially. But then you can also in the higher order you can also draw, if at E square, this is at E square, let me call it, and potential, this is e power 4, or this is at leading order, this is a leading order. This is at next to leading order and NLO essentially next to leading order, next to leader. So you have 2 photons which is exchanged. Okay, there could be other diagrams also, because you can have in next to leading order there will be several other diagrams. Why only this? You can have 1 photon exchange like this, the other photon sitting like this. Okay, exchanged and photon. Okay, you can have, okay, this is also e power 4. There could be other diagrams in which the electron positron pair is exchanged inside this. This is also e power 4, because remember we are always changing, we are always doing perturbation order by order essentially. Now this blob you can put it here, this blob you can put it here, this blob. So you can have boxes, these diagrams are called boxes, this is called something else essentially. This has a particular name, it is called vacuum polarization. I will tell you why it is called that. It is very interesting essentially, you can derive a potential for it essentially, and for the vacuum polarization there is some potential called Uling potential and everything. And then you can have, so coming back to our thing, then you can have this is called self energy. Then you can have a diagram so this is called vertex corrections. So simple process will have all these classes of higher order diagrams essentially. So all these classes of now there is interesting theorems in QED, okay, which tells you that if you take care of, okay, which now what is the problem with these diagrams? What is the problem? What is the problem with these diagrams? The problem with these diagrams is, let us take one particular example, okay, simple example, okay. So this also happens in other examples also. Let us take the momentum structure of any of these diagram. So for example, let me take this vacuum polarization diagram. I will take the sub diagram of this. So this has a momentum q, this has a momentum q. What is the momentum in between? This is k minus q, k plus q. So okay, this has a momentum k essentially. So this has k goes in, k plus q comes in essentially, comes out. It has a momentum k. Now what are the constraints on k? The momentum k. Now these momenta, the q momenta are constrained because they depend upon the energy of the external lines. So you are having photon, there is a P1, P2, P3, P4. So q is determined by, okay, q is fixed by your external momenta P1, P2, P3, P4. Q is fixed by external momenta. Q is fixed by external momenta, whereas P1, P2, P3, P4. So their energy momentum conservation fixes your Q. Now what fixes K? K is completely sort of arbitrary essentially. So what values should K take essentially? Okay, what values should K take? Okay, so the K, if you want to calculate the K part, essentially let me just calculate the K part, forget about the full thing. There are two, there is a propagator, pion propagator, let me just call it as pion propagator, the photon propagator. The photon propagator has a correction coming from this loop essentially, which is this is a p k slash plus m f by k square minus m square times q slash plus k slash plus mf, which is the fermion mass, by q plus m whole square by mf square. Okay, this is the contribution of the bubble. So this bubble's contribution will go like this, the momentum contribution. Now this bubble's contribution you have to put in limits, because you have to put in integrals essentially. What is the value of k? K is completely unconstrained, it is a virtual k, these are virtual particles, completely unconstrained. It is completely unconstrained, so this should go as minus infinity to plus infinity d power 4k. So this is called a loop integral. this is called a loop integral. This is a loop, okay. This is also, this is a box. So box is also a loop, essentially kind of loop. So all of these are loops essentially, this is a loop, this is a loop, this is a loop, this is a loop. So in higher orders you will end up having this unconstrained k, a new integral which is coming because of the unconstrained momentum, okay, because of the unconstrained momentum of the virtual particles. So this k is not fixed by any of the external momentum. So it can take any value it wants essentially, it can take any value it wants, and that is the reason this is called a loop integral, and that is one which appears in every higher order diagram essentially. That is the one which appears in every higher order process. In every higher order, second order in perturbation theory, this loop integral will appear essentially. Not exactly this form, okay, not exactly this form, but in depending upon the, if bubble has this form, the other one has another form and everything. Now the limits of this integral are large k. Now if k is very large, you can neglect mf and q and everything, okay. Okay, if k is very large, so you can see what is this thing will look like, okay. How does this integral, whether the integral diverges or converges. So the integral, okay, the integral has at large k has the form integral minus infinity to plus infinity k square on the top, you can just take it, forget about everything, dk by k power 4, okay, has an integral of the form minus infinity to plus infinity k square d power 4 by k. Now d power 4 you can do, d power 4 k can be, you can write it in terms of say spherical polar coordinates, essentially you can write it in terms of spherical coordinates. So this will be, so d, okay, there will be k square form, k power 4 times some angular factors essentially. So this will be d power 4 will be in higher dimensional spherical polar coordinates, higher dimensional. So this will be equivalent to d power 4 can be, will be written in terms of k power 4 times some angular coordinates. So this integral will be k power 6 times some angular part by k power 4, and this integral is roughly goes as k square. So this integral is divergent and it has an infinity at uv, at very large k, okay, this integral goes to infinity. It is not a convergent integral, at very large k goes to infinity. It touches infinity because it goes as k square, right, essentially k square divergent. Such integrals are called quadratically divergent. Now the process of isolating, okay, now you need to get physical results out of this. So to get the physical results you do two particular things. So this means that your at higher orders your theory will be having infinities you have to deal with. Either you deal with, you say that okay my theory is unphysical at higher orders, or maybe this is just a fictitious thing, okay. It is fictitious because the way we are doing the theory, okay. Why it is fictitious? This UV and everything, these divergences are fictitious is because you are using free particle wave functions all through, okay. You are using free particle wave functions completely. The method you are calculating this process is you are using free particle wave functions. Where is this process? Okay, this is a free particle, this is a free particle, this is a free particle. When you are solving solutions, you are using free particle wave functions. So that means, but in the presence of interactions, even when the interactions are present, you are neglecting them and using free particle wave functions. So the presence of these infinities is not physical, but it is just the way it is telling you that the methodology leads to these problems. The methodology of the perturbation theory methodology we are doing leads to these problems, essentially because we are using free particle wave functions, free particle Green's functions, everything, essentially everything is free particle, but you are multiplying at one particular vertex at one particular space time point. This methodology at higher orders will always lead to these infinities, okay, these infinities. So and these infinities have to be dealt with, okay. So I think I convinced you that, so instead of solving, nowhere we solve the Dirac equation in the full presence of interactions. We solved it always, all the wave functions and everything we are using, okay, are free particle. Are more because of the presence of the use of free particle wave functions and propagators and free particle wave functions and propagation and perturbation theory they are fictitious and should be removed away. So the how you remove them, so how you remove them, there are two methods of removing them, there are two steps in removing them, one, okay, one is that this infinity has to be isolated in the integral. There are various methods of isolating this integral. There are cutoff methods, polyvillars, there are various methods, and this process is called regularization. Okay. This process is called isolating the infinity in the loop integral is called the regularization. The second thing is a process called renormalization, okay, in which the wave functions, okay, you absorb the infinities. See, the wave functions which you are using are not physical, you are using wave functions which are unphysical, because what you are using is So, because it is unphysical, it is some sort of a wave function which does not have which is not done in interactions essentially. So, the wave functions physical is equal to psi plus the infinite term essentially. So, infinity okay. So, you absorb this is called the bare. What you say is the bare wave function is nothing but the infinite part. This also can be written in terms of multiplicative form into psi bare essentially. So, this is the renormalization constant. So, you do the same thing for all the parameters of your theory. The coupling constant is equal to G0 plus, so the some renormalization correction essentially the infinity. I can write you the expressions, but anyway this is gives me the renormalization, and the coupling constants, wave functions, everything you have to do it essentially. Masses where this is the physical mass times the infinity, which is we can call it as some m bar or something essentially, okay, which contains the infinity essentially. So, all the parameters of the theory absorb these infinities order by order. All the parameters of the theory absorb the what we initially call the say wave functions are sort of to be the unphysical or the bare, okay, or the bare infinities which are absorbed essentially because they are not physical in principle. What is physical is your cross sections and your what are physical are your cross sections and your decay constants. These are your physical quantities. You do not measure your wave functions, okay, in theories essentially. In fact, you do not even measure your coupling constants in your thing, but you can infer your coupling constants in particular thing. You can measure your masses, okay, but the masses also change because of this process. What happens is one of the interesting process of the renormalization is that the coupling constants and masses change with energy. These are renormalization scheme dependent. There are various schemes of renormalization. These are renormalization scheme dependent, okay. So, but these are interesting. For example, the strength of the coupling, so the renormalization is actually a physical phenomena in some sense, in the sense that as you probe with higher and higher energy, okay, as you probe with the coupling constant becomes small actually. The coupling constant becomes larger and larger in QED. The coupling constant becomes larger and larger QED. So, for example, at energies which are around MeV, the coupling constant alpha is 1 by 137, whereas if you take Q square is 100 GeV square essentially, okay, 100 GeV square, alpha becomes 1 by 128. This has been experimentally proven essentially. Why this is happening? This I think I explained this previously, because what you are seeing is finally the cross sections and these are your decay constants and everything. But what is happening is because as the energy probe, as the energy of is increasing, because here the Q square is increasing, as you increase the Q square essentially, as you increase the Q square of probe, I think this plot I have plotted some time ago, you produce lot more electron positron pairs around the particle essentially. You produce lot more electron positron pairs, and so you see the effective charge increasing, and the effective charge keeps increasing with energy essentially. This is the the reason why there is a renormalization happening essentially. This is the reason why there is a renormalization happening. So you start with a probe which is some energy, but as you keep increasing the energy you create more and more electron positron pairs, and these electron positron pairs will be aligned in particular direction, screening the charge, and so this is the reason why the coupling constant keeps changing. Now these coupling constants are also not physical, because meaning what we feel masses are physical, there are particular masses which are physical, which are called pole masses, which is what we mean by the mass of the electron is 0.511 MeV essentially. Me is equal to 0.511 MeV. So these are called pole masses, in which it is the pole of the propagator, but other masses which are renormalization dependent masses, they run with energy. Similarly the coupling constants actually, okay, you define the coupling constant when the energy is going to 0, essentially when the energy is going to 0, that is when you define your electric charge, the coupling constant, and so on. So and then that is your sort of your physical energy charge, electric charge, and so on. So but when you have momentum dependence, you have some other kinds of charges, renormalized charges, which keep running with energy essentially, which keep running with energy, which takes into the effect all these things which I have mentioned essentially, all these things. So to summarize, the higher order corrections typically involve loop diagrams. These are loop diagrams, okay, these are loop diagrams. So and these loop diagrams involve integrals which are contain typically divergences. These are divergences, but these divergences are not physical, because they are artifact of the perturbation theory we are using. The way we use the perturbation theory with only free particle wave functions and completely neglecting the interaction picture and everything. So these divergences have to be dealt with. Okay, the way we deal with these divergences is to isolate them first essentially in the integral, and then absorb them into the parameters of the theory. And this can be done because the parameters of the theory, like the wave function, the coupling constant, and masses, and or just are not the physical masses essentially. What we measure are the physical masses, and the physical masses which we measure are different compared to what appear in the Lagrangian, essentially what appear in the Lagrangian. So these parameters are converted into physical parameters by absorbing these infinities essentially by these by multiplying by some constant which are called the renormalization constants, okay. And this is the process of renormalization, which will be dealt in a hopefully in the next series of lectures, which I hope to give on quantum field theory essentially, on quantum field theory 1. So throughout this lecture series what you have learned essentially is that you have learned Green's functions methods. So you have used the Green's functions methods to calculate leading order calculations in QED. You have understood the concept of propagator, how to derive the propagator using Green's functions methods. So and all these things which are old, looks like old topics, are now being revived in terms of concepts which are like dark matter or something, where we do not know anything about the interaction essentially. These things are being revived in these particular cases, and there is one important topic which I will cover in the next class, which is about relativistic corrections to non-relativistic systems, which is exactly with which we close this course essentially, which is nothing but calculating relativistic corrections to the hydrogen atom, okay. So with that we close this course, okay, and thank you very much, okay. If you have any questions you can write to me on my email, which all of you have essentially, okay. Thank you very much, thank you.